This recording is about the Grid Services Study, specifically recorded for focus groups and future viewers who are interested in learning more about the Grid Services Study, what grid services are, and how they may be a potential grid solution in Massachusetts. To set the stage, the Massachusetts Clean Energy Center is the clean energy economic development arm of the Massachusetts state government. MassCEC is focused on strengthening and supporting the Massachusetts economy by catalyzing the innovation needed to meet the state's ambitious climate goals. Our Net Zero Grid team is focused on fostering innovation on the grid for the energy transition. As most of us are aware, the grid will be our platform for decarbonization. There are a lot of changes, though, that the grid needs to get there and to be able to be that platform. For a successful, equitable grid transition, we'll need a lot of new technology, new ways of working, new business models, new programs, etc., to help us get there. Our Net Zero Grid team's approach is that earlier and deeper collaboration with utilities and grid stakeholders of all kinds are critical for the grid's transition to meet the state's climate goals and to develop into an equitable energy system. This concept of earlier and deeper collaboration is certainly relevant when working on new and innovative models like this work, the Grid Services Study. MassCEC convened this collaborative group that you see represented on the slide for the study. We all work in close partnership on this work. We have our Massachusetts Net Zero Grid team and representatives from state agencies, the Department of Energy Resources, and the Attorney General's Office. We also have representatives from the 3 Massachusetts investor-owned electric distribution companies, or EDCs, or utilities, Eversource, Unitil, and National Grid. And this work is being supported by consultants, the Rocky Mountain Institute, RMI, and Energy and Environmental Economics, E3. We're going to spend some time introducing the Grid Services Study, but we're going to do that by way of first talking about the context of this study and work. I'll start by talking about how the grid traditionally has worked, including what it was built for and how it responds to new electric demand. And then we'll talk about what makes right now a very unique time and the main questions that are emerging. We'll then talk about what distributed energy resources, or DERs, are and why they are a potential solution to those questions. We'll move from there to discuss some examples and conclude with a high-level introduction to the Grid Services Study. The grid works as follows. Electricity is generated at a large-scale facility owned by private entities and then moves through the transmission system, which we can think of like a highway for electrons. These electrons move fast and they travel long distances. Then the electricity goes to a substation where it is slowed down like an off-ramp from that highway. And I'll circle back to substations in a minute. And then it moves through the poles and the wires that we see in our neighborhoods, eventually to our homes and businesses, which are the end uses, or we call them loads. The distribution system is the part of the grid that distributes electricity to its final destination. It's the part of the electric grid from our substation through to our homes and businesses. And this is how the traditional grid has worked. It moves from generation to transmission to the distribution system, which again is our neighborhoods, homes, and businesses. For this work, the Grid Services Study, we are focused on the distribution system, which you see again in the orange box below. The distribution system is the part of the system that your utility, Eversource, National Grid, or Unitil owns and manages. Circling back to substations to share more about them. Substations take a lot of forms and sizes depending on the need, but they all act like hubs or off-ramps where electricity is passed from the transmission system to the distribution system and stepped down to safe, slower voltages. Substations are a necessary component of grid infrastructure and do not produce emissions. but they do take up space and they are expensive to build and maintain. Here are some examples of substations that probably look familiar to ones that you see in your neighborhood or when you're driving around. But there are also some that are indoors or underground, as you can see shown in the picture on the far right. So what was the electric grid originally built for? The electric grid was designed and built to support things like our light bulbs and refrigerators, computers, fans, AC in the summer, and these are generally considered small loads or electric needs. The last thing that I want to talk about relating to the traditional grid is how the grid historically has dealt with load growth or when more electricity has been needed. Historically, the grid worked like this. When more electricity was needed in a town, say a new housing complex or a new commercial area is being built, the utilities would need to build or upgrade infrastructure like a substation to make sure that the homes and businesses had access to the power they needed. And this traditional solution, while it can meet the customer's needs for electricity, like enabling that commercial area, it does have challenges associated with it, including the fact that building new infrastructure costs a lot of money, which also, of course, impacts electric bills. It takes a lot of time. Some of these projects can take years. And it also requires things like digging up our roads, closing streets, hosting noisy construction sites, potentially using new land, and not to mention additional greenhouse gas emissions associated with this construction. And then more generally, the energy system has burdened certain communities disproportionately. So let's put the way the grid has worked historically on pause for a minute and think about today's unique context. Today in Massachusetts, we are expecting electricity demand to soar as we transition to a clean energy future. By 2050, we expect electric demand to double. We are trying to remove fossil fuels from our businesses, our homes, and cars. But to stop using fossil fuels, we need to use electricity to electrify them instead. So the amount of electricity we needed in the past to support our light bulbs and refrigerators and ACs, everything that we mentioned, is going to pale in comparison to the amount that we're going to need to electrify our homes and our transportation. So if that traditional solution used to meet our increased electricity when it was serving only light bulbs and ACs, these small loads, if that was expensive and took time, then we can begin to understand how expensive and lengthy the situation might be to meet the future electricity needed to power all of our homes, transportation, and businesses. So not only is it going to be costly, but there are expected to be situations in the future when utilities can't even build fast enough to meet the timeline of when the electricity is going to be needed. The utilities have already identified areas where electric demand is expected to outpace the current grid infrastructure in that area, and they know that some solution will be needed to meet that demand. This picture on the slide is from National Grid, and the image on the left shows substations today. So we can see that there are a lot of green and some yellow or orange, but essentially this picture is telling us that today's substations are meeting today's electricity demand. As we move to the picture on the right, however, which is 2035, if there is no change to infrastructure, we can see that these substations, many of which are now red, will be unable to meet the electricity demands around it. The utilities have plans, though, to make sure that some of these don't turn red, and that means certain construction projects to be able to meet capacity. However, there are other ones, as I mentioned before, that meeting the timeline of need with construction is going to be very hard. We are facing a future with unprecedented demand for electricity, and that's what makes right now such a unique time and a turning point. And as a result, there are emerging problems or questions for us to solve. Questions like, what new solutions exist or can be used to meet this demand? And also, how do we make sure that future solutions contribute to a just and equitable energy future? One potential solution is the use of technologies referred to as distributed energy resources, or DERs. DERs are technology like solar of all sizes, batteries, etc. And we can also consider the smart electrified devices in our homes and in businesses to be DERs, our EVs, heat pumps, and even appliances like water heaters. So we can think of DERs as sources of energy that are spread across the distribution grid. So let's return to the picture of how the electric grid worked in the past. To review, we have generation occurring in those large-scale facilities owned by private entities, and then flowing through transmission and ultimately through the distribution system where it flows to our businesses and homes. The main highlights are that electricity originated in a large-scale upstream source and flows in one direction. But with DERs now in the picture, today's grid, or the future grid, starts to look more like this. We see highlighted in a darker gray box below is the distribution system, within which we have many different DERs that are capable of not only taking electricity, but also giving electricity, or using new smart technology like a thermostat to turn down to leave electricity for other sources when the system needs to free it up. And to put this in contrast to the grid before, we have sources of energy now that occur throughout our distribution system versus before when they only fed into the transmission system. And we have the flow of electricity occurring in more than one direction. So why are DERs a potential solution? As we saw in the earlier diagram, DERs can be located in many places across the distribution system. DERs are also able to use and release electricity onto the distribution grid, and in some cases even generate electricity. By releasing electricity, we can imagine a battery discharging, and by generating, we can imagine a solar panel generating or creating electricity. And DERs are smart. They are capable of changing the amount of electricity that they take or give. So for example, somebody can tell their car when to charge and when not to, or a big retailer can trigger a huge heating or cooling system to ratchet down if it's causing too much strain on the grid on a hot summer day when the other buildings around it also need air conditioning. Let's move into an example. Here is a depiction of the grid that's similar to the ones we've discussed earlier. Only this time we see two different substations. Substation A is electrically connected to this distribution system to the right. We can think of that as one town or neighborhood. And substation B is connected to another. The utility predicts that substation A will, in the future, no longer have the ability to meet the electricity needs that it serves because the majority of the houses and businesses are installing heat pumps. So there's a future constraint. And the utility could follow the traditional solution of starting construction to solve this future problem. Or the utility might be able to defer the construction project or even not need it if they could identify DERs that are electrically connected to substation A. So let's take a look. In this example, the utility looks and sees, yes, there are enough residential and commercial DERs electrically connected that can help alleviate this constraint. And importantly, The utility would not be able to use any of the DERs connected to substation B, as there would be no value received by substation A, even if those houses or businesses seem geographically close to substation A. They need to be electrically connected. So to emphasize, the location of the constraint and the DERs matter. In other words, there are ways for these DERs, these technologies, to help the grid in a specific neighborhood or area and potentially avoid costly infrastructure upgrades or delay the need for those upgrades and meet the needed timelines. So this location-specific help that the DERs provide, like releasing electricity from a battery, is often referred to as providing services to the grid and is ultimately termed grid services. Let's look at this idea another way. There is a specific neighborhood on the distribution grid that the utility predicts will need more electricity in the next couple of years. Traditionally, the utility would have to do a construction project, which costs money and has the other associated challenges we discussed with it, and that cost ends up in our electric bill. But with DERs as a potential solution, they may instead be able to pay those DERs for the grid services, which will cost less, and then less money goes into our electric bills. In other words, there's an opportunity for ratepayer savings. DERs can give us another pathway where we might be able to address some of the challenges meeting new electricity demand. Sometimes grid construction will still be the best solution, but there are also places where DERs could provide a very good alternative, either to bridge a gap in the timeline or to defer or avoid the construction. So we know that DERs offer a potential solution and add value to the specific places on our distribution grid, but how do we unlock them and harness them? This grid services is a starting point in answering that question. We know we need a way to compensate DERs for their reliable services to the grid, and that compensation needs to not just be fair, but also needs to ensure reliability, that those DERs are going to show up at a certain time and place when they're asked to. For example, the utility wants to know that the specific house or businesses are going to be able to dispatch their DERs when they're asked to. This compensation piece, how to pay DER owners and operators for a local, time-bound grid service, is what the study is primarily about. And because this idea of DERs providing grid services to the distribution grid is at an early stage, we want to start opening the conversation to a diverse group of voices to help ensure that any solutions that develop out of this idea over the next few years and decades build towards an equitable energy and grid future. If you're familiar with connected solutions, the grid services study and future offerings from it are a similar idea. You have devices in your home that you can enroll in your program, and you don't notice it, but after you sign up for the program, the utilities can make minor adjustments to change how you're using energy and in ways that help the grid. But there is a key difference, which is what makes the grid services study and future work particularly valuable. Connected solution asks people or DERs to respond and provide a service when the system across many states is peaking. And then when the people or DERs respond, it helps minimize or limit the peak. The grid services study, however, focuses on local peaks or constraints. So there's a specific substation or piece of infrastructure with a constraint, which means only specific DERs can provide service or value back to the grid, even though all ratepayers can benefit. So we want to make sure it's clear the expectations on timing. We are here. The work on this grid services study helps to build the frameworks to guide the utilities on the future of grid services in Massachusetts. We're answering questions like, how much money can this save customers? And how do we pay people enough to get them to reliably participate? And we're starting to socialize the idea with stakeholders and gather input. After we build the frameworks, the utilities will begin to do initial trial offerings later this year. Then, over the next 5 years, they'll continue to try new types of offerings and locations. They'll learn over time what works and what might not, and gather information on how grid services fits into the bigger picture for the grid. 5 years down the road, they'll file a new plan and update with DPU. They'll have information under their belts and be able to take next steps of designing. What does a scaled version of grid services program look like so that it can be valuable in many places? We don't expect a full-scale program to be available until 2030 or beyond. And there are several touch points along the way where you can learn more and have influence on the process. We have a few more months of the grid services study and more workshops, and then some communities will be in areas where grid services have offerings. Through 2025 and 2029, the EDCs will file biannually with the DPU with updates. The Grid Modernization Advisory Council and the Equity Working Group will also monitor and collect data. At each filing and in the 2029 updated plan, the public can participate. If you want more information on DPU participation, the agency has good resources to guide.